Okay, I guess we'll have a few questions now from the audience. We'll probably do some online ones first, though. So we've got some questions from online. Someone asked, what else can your models tell us about stars?
What else can the models tell us about stars? Well, they tell us so we can take, right, we can take this little baby star cluster here, right? We can observe literally every single star in this star cluster, right? But when and so this lives probably within our Milky Way or LMC or SMC. We can't resolve individual stars past that. Distance is more, so galaxies is more distant than that. And when we go to galaxies like this really cool galaxy here, this is called Hogg's object. It was discovered by someone named Hogg, right? We don't have the resolution to observe individual stars. And so we have to like get our models, and we have to start to take averages and complex, summations of things to go and see what we know about individual star. Can we describe processes that happen on a global galactic average? It's kind of like, saying, well, what's the age of everyone in this room, right? We can come across one age. Oh, the average Australian is, actually, I don't know how the old average Australian is. We're going to say 36. I actually have no idea. Is there someone in this room who's 36? Maybe. Is there someone to be older? Yes. Who could be people who are younger? Yes. And so by studying the individual things, right, individual people, we can learn more about the global properties.
Fantastic, thank you. And someone else has asked, so how are stars born?
How are stars born? So stars are born when we take gas clouds, just big clouds, hydrogen, helium, a little bit of everything, and we just collapse them, and they condensate on themselves, and then because gravity is this attractive force, right? It just brings things together, and it'll just bring them together. And then as that happens, as we were talking about earlier, when things compress, right, the atoms get hotter because they're moving faster, the density, and we just reach a point in time of where we can just start fusing. And that's by definition of a star.
Awesome, thank you. And going back to, I guess, the telescopes and observing and the Hubble Space Telescope, Callum has asked, how does the Hubble Space Telescope stay still long enough to take pictures if it's moving so fast?
Okay, this is excellent, right? As I said, Hubble Space Telescope moves 27,000 kilometers per hour. So it just points in one direction, right? So it'll just point for 45 minutes, and then it'll just do nothing for 45 minutes. It's actually beaming down all the information because it can't move that fast. And it has a pointing accuracy of a human hair at half a kilometer away. So we can take half a human hair, right? I should say half a human, so it's even smaller, and point it out, put it half a kilometer away, and moving at 27,000 kilometers per hour, it can observe that and stay focused on it. It's very amazing. Basically, computers really help us put these images together.
Yeah, wow, it's pretty amazing. And I guess final question, what is your favorite part of, final question for online, what is your favorite part of about being a scientist?
I would say my favorite part of being a scientist is I'm a scientist here, and I do stuff like this because I really like to look at pretty images and get paid to do it, and that's super great. And we're getting images of things that are millions of light years away, and and I get to be the person that figures out the physics of how the universe is working for this exact object, and I find that really exciting.
Awesome, thank you. Do we have any questions from in-person people?
Oh, do you want me to pick on people?
No, I can do that.
Yes, you said that the photons are very old, that they come from the pictures,
Yes,
right?
yes.
So I learned that all the galaxies are moving. So
Yes.
So the next time we take a photo of that same spot, will it be like somewhere else?
So remember, things are millions and millions of light years away and millions of years old. And in our human time scale, right? 5, 10, 15, 20 years, things don't move that much, right? Because that's like a blink of an eye, right? In the universe.
And what about over there?
How do they think decide that?
Oh, this thing?
So what's the question?
So the question is for this image, it's called Planetary Nebula here. How did the rings happen?
Bottom right.
So what's happening is this inside here is a star, kind of like our sun, that died and it basically exploded. And so these are just basically the rings of the exploded star propagating outwards. So it happened in like jets. Yeah.
Since you did your Hubble,
Yes.
are you looking forward to what's happening to
Yes. Yes. So the next big space telescope that's going on between NASA and European Space Agency, ESA, is called the James Webb Space Telescope, and it's observing in the infrared. So Hubble was using the optical, and James Webb will be in the infrared. And yes, I do have I've heard some teams that will be getting some time on that. Yeah, on the first second. Yes.
I am slightly.
No.
But I was just interested in looking at Hubble. How is it being serviced now, or is it just at the end of
Okay. So the Hubble Space Telescope is no longer being serviced, right? Because the U.S. retired its shuttle program. So 2009, which was its last servicing mission, which is almost 11 years ago by now. But when they did that, they replaced all the cameras and they replaced all the gyroscopes. So right, there are 3 gyroscopes, for in all 3 directions, and everyone has its own backup gyroscope as well. And so in theory, if one breaks, actually last year a gyroscope did break and they couldn't fix it. And we just do what we always do with electronics. They just powered it down and powered it back up and it fixed it. It's kind of amazing. So yeah, but once it's broke, it's broke. Yes. Yes, so radio frequency, let's see, should I go to this back to a slide? So light is a super weird thing because we'll go back here and also show you as well. Light is a super weird thing, right? Because it happens in both, it's a wave and it's also a particle at the same time, the wave particle duality. For when you take quantum mechanics, you have to know this. So when we're talking about, the visible and the ultraviolet, right? This is really talking about, like we're capturing individual photons. Like, you have your camera on your phone, you can take an image of something. We're capturing individual photons of light on the camera, right? On the detector. And when we go to, say, radio, this is kind of what you're talking about, right? When we go to radio, right? We're more talking about looking at light as a wave. Has anyone ever been to like the Parkes telescope? Yeah. Yeah? Anyone know what was so famous about the Parkes telescope? Yeah, that's how we observed when the astronauts first landed on the moon. It was sent around the world with that and honeysuckle here in Canberra. And that is, there are these big dishes, right, meters and meters in size, and if you go and look at them, they're actually literally just a mesh. Like there's not even like a mirror camera. It's just like wiring, right? It's because we're just collecting light as it comes in a wave that's meters in size. And then we can build things like interferometers, if you've ever heard of those. We're just have a telescope here and a telescope there, a couple kilometers apart, and those just add up into light. That's how we end up with a 100-kilometer away. Yeah. The image of when we imaged the supermassive black hole in M83, I believe, that was actually we actually turned the entire Earth into a telescope. So that's big telescope. More questions? Was there a question over here? Do we have a question here? Oh, you forgot it? Okay. Yes, question.
Me?
Yep.
Okay, so this is kind of about the galaxies. So like the black hole in the middle,
Yes.
it can keep everything spinning around it.
Yes, well, the black hole doesn't keep things spinning around it. The mass of the galaxy keeps things spinning around. Right? It's kind of like a pizza, right? If you ever get a pizza dough ball, what happens when people in movies, I don't do this because, I'm not very coordinated, when they start to flatten this dough ball and turn it, right? It just flattens into a disc, right? Rotating disc. It's basically what a galaxy is, a rotating disc of stars.
Yeah, well, like, how does that can bring another galaxy towards it?
So galaxies just have random motions, right? So sometimes they'll be gravitationally like bound to each other, like the LMC, the Magellan Clouds, and the Andromeda Galaxy. We are just, right? Gravity is just an attractive force. It brings things together. So even though there would be, millions and millions of light years away, they were slowly with time just be gravitationally attracted to each other. Yes.
So the gamma rays,
Yes.
aren't they like too powerful for like anything to resist? Like if we show the gamma ray into the floor right now, it'll like go to the
Yes. Yes. Gamma ray telescopes are very, so we do have telescopes. We have to go to space to detect gamma rays. And basically there'll be telescopes of where you have a ring of mirrors, and then inside it you have a ring of mirrors that has like a slight angle to them. And so just basically you have this constant like mirrors of where it just goes and makes them all the gamma rays collide into the same point of your detector. It's very cool.
Awesome. Okay, I think we should wrap up there, and let's have another round of applause for Katie.